Hello, and welcome to Lecture 3 on the topic of electric potential. Okay, this is the third lecture in our discussion of electricity and magnetism. Here we're talking about electric potential energy, okay, and then something called electric potential without the energy, okay? We're going to talk about the units of those terms, how they relate to things we've seen before, and how they relate to other concepts in electricity. Our objectives are to understand the difference between electrical potential energy and electric potential. We want to see that the work energy principle and general definition of work applies to the Coulomb force just as to any other force, like the gravitational force. We need to learn to recognize and interpret the electrical potential of a point charge or a small group of point charges as a very important special case, and be able to draw equipotential lines. Okay, so let's get to our key terms and a lot of conceptual understanding. I don't think the examples are that difficult in this lecture, in this half of this chapter, introducing electricity, but I think the concepts do deserve a little bit of time to make sense of. Okay, so let's look at the first key term, the electric potential or electrical potential. Now, you've probably heard the term volts, okay? Well, volts are electrical potential. A volt is the unit of electrical potential, and sometimes we just refer to electrical potential as voltage, okay? That needs to be understood. Those terms are synonyms. I will use the terms volts and electrical potential interchangeably. What is it? Electrical potential energy normalized by charge. That's what a volt is. Now you remember that term normalized, it means divided by. It means I've taken electrical potential energy, which would have units of joules, and have divided by charge in units of coulombs. That gives us the unit of the volt, a derived unit, okay, represented by the uppercase V, the volt. Very important unit in electricity and magnetism, but not a base unit, okay? Now, neither are joules and coulombs. They're not base units either. You may remember that the joule is the kilogram meter squared per second squared. And since we have to deal with so many different units in electricity and magnetism, let's consider the dimensions of the volt. It is the mass to the first power, length to the second power, time to the negative third power, and current to the negative one power. And again, that's just because current, represented by amps, but current is just charge over time. Okay, just charge over time. All right, excellent. So there's our basic definition, the volt. It's normalized energy, okay? It is related to the electric field, absolutely, but unlike the electric field, voltage values are scalars, okay? Now, that's important because, first of all, we should expect that because we're talking about energy, and energy is a scalar. Second of all, it's important because the method of solving problems with scalars means you don't have to ever consider direction, which means you never have to consider right angles and take components or any such mathematical work. Scalars are inherently easier. If you recall, when you learned about energy in your semester on mechanics, that, well, working with conservation of energy problems was often an easier way to solve problems that could be done with forces and kinematics. That idea holds true here as well, because scalars are easier to work with than vectors. Furthermore, conservation of energy allows us to solve for values of displacement and velocity without considering the path. For systems where we would not be able to find the time it takes to go from point A to point B, you can still find how fast you're going at the later point. If that sounds familiar, great. If it doesn't, please review mechanics. Okay, now I do want to call up this idea of normalization and make a comparison with another quantity we just saw and was just mentioned, the electric field, and that's the following. Zoom in on this a bit. The Coulomb force divided by Q gives us the electric field. In fact, the vector of the Coulomb force divided by Q gives us the electric field vector at that same point. Okay, after all, the electric field is a vector field. Okay, well, that idea of dividing by Q is the same idea here. We have potential energy with the subscript E to represent electrical, and we divide by Q, and we get voltage. See the comparison? It's very common and useful to divide by charge in order to discuss quantities like electric field and voltage, because now we have a map, like these pictures here, that is independent of what you put in it. So I could drop an electron, or I could drop a proton, or I could just drop any charged particle wherever I want, and that map will tell me the electric field strength, its direction, and the voltage, independent of whatever I put on that map. See, it's normalized. It makes the map a complete story that you can work with. Okay, you can solve problems with it, and you can interpret it. Well, this takes us right to the idea of equipotential lines, because these maps here have equipotential lines on them. Now you might say, okay, well, this looks like something you've seen before, but just busier with more lines and all these dotted lines. Well, you might have guessed it. The dotted lines are none other than the equipotential lines. Now the blue lines with the arrows on them, well, we've seen those before. What are those? They're electric fields, okay? All right, it is a vector map. It has direction, as noted by the arrow, right? It's not a single vector, but a bunch of vectors. And if I put, as I said before, a charge at any given point, the electric field would tell me how strong a force that charge would feel if I know the strength of the charge that I placed. And importantly, it would tell me the direction that it would move. Okay? And as far as direction, you need to know if it's, of course, positive or negative. Okay? All right. Now, those are the blue lines. The dotted lines are the equipotential lines. Okay? So now we have this way of drawing the effects of charge distributions, like two positive charges, or a dipole with one negative and one positive charge. The effects of these charge distributions, these charge arrangements on their surroundings, represented simultaneously with electric fields and equipotential. Why would you want to do that? Why would you want to draw both electric field and equipotential lines? Is it really necessary to do both? I would argue yes, because by drawing both equipotential lines and electric field lines, you have a very fast way of thinking about the effects of those charges, how they would affect other charges placed nearby, how those other charges would accelerate, where they would go, in what direction they would go. Okay? So, equipotential lines are defined as lines that represent curves of identical voltage. That's the equal part, the equi part, right? So anything along this line here would have the same voltage. We'll talk about how to calculate that voltage in a few moments. Okay? All right. They are always perpendicular to the electric field. So if you need a handy way of drawing them, you have to remember that they cross all the field lines, always perpendicular. See? Okay, that's always true, no matter where you are. Okay. Note that equipotential lines are scalars, unlike electric field lines. They're both called lines, but that betrays the fact that they're very different. One set of lines, the blue, in this case electric field lines, are vectors, okay? The dotted black lines are just scalars. Got it? Now here's an analogy that has nothing to do with electricity. Think of the equipotential lines as as elevation on a map, and the electric field as directions water would flow downhill. Think of that. Imagine that this is an elevation. This is, say, 1,000 feet. All right, that means that this equipotential line here, since it's going uphill, would be maybe 1,200 feet. These are elevation lines on a topographic map. And then what topographic maps don't typically have then would be the watershed directions, where water would flow. In other words, if you started water here, it would flow in this direction. On the other hand, if you started water here, it would flow in that direction. See it? Okay? So I think that's a very great way of being able to visualize, interpret, and make sense of this information. Okay? So let's get on to the key formulas. Okay, so first of all, we have three expressions for work done by an electric field. Now, why did I put the stress there on the word by? Well, because anytime we talk about work, and this was true when we talked about work done by gravity or work done by an external lifting force or work done by a heat engine or work done by the surrounding environment of the heat engine. Hopefully these ideas sound familiar. Whenever we talked about work, it was always so important what was doing the work, whether it was an external force or the force that created a potential energy. Okay? Again, review mechanics to make sense of these ideas. And that's true here too, very much so. Okay? And I'll have some examples to illustrate those ideas in a moment. But let's look at the work done by the electric field. Okay? Well, let's consider a uniform electric field. Okay, so this expression here, I've taken an arrow over here to show that we're considering a special case of a uniform electric field. This is the work and potential energy change in a uniform electric field, like the one shown here between a capacitor. We'll be talking more about capacitors. It's an idea we've hinted at a bit, but we'll be getting into it in some depth later in this very same chapter. But a capacitor is such an important concept because it creates a uniform field where other situations can't create an approximation of a uniform field, and we want that approximation. We want that simplification, a nice uniform field wherever we go, it's the same strength and the same direction, wherever we look, okay? And that's nice because that allows us to, say, allow particles to move through this field and track their motion, okay? It creates constant acceleration, very importantly. And the idea here is we're going to consider the energy effects of this uniform electric field. Because if the electric field points in one direction and we consider a displacement like the one shown here in a slightly different direction, then the angle between the two will give us work. Again, think gravity. Think about doing work at some angle to gravity. Think about doing work at some angle relative to any general force. It's the same idea here, and it is a uniform constant force. And that means we can simply use the definition of work as the force, the displacement, and cosine of the angle between the two. And let's go ahead and label those variables. So F sub c is the Coulomb force of the uniform field. The field strength is E. The charge moving through the field is Q. All right. And D is the displacement within the field. And last, theta is the angle between the displacement vector and the electric field vector. And sometimes they're parallel, in which case the angle would be 0. And cosine of 0 is what? 1. Okay? Because if the charge is moving parallel to the field, then the work done by the field would just be QED. On the other hand, if the charge is moving exactly opposite the field, then the angle would be 180 degrees. Cosine of 180 is -1. And then the work done by the field would be negative QED. Okay? And then let me then call attention to the important difference that we would never have seen of gravity is since Q can be either positive or negative, that means that negative QED can become positive QED if the charge moving is negative like an electron, because the negatives would cancel out. But that, of course, makes sense, because an electron moving opposite to an electric field is actually having work done on it. Whereas, of course, an electron moving with an electric field is, well, not having work done on it, not positive work at least, okay? The field would not be accelerating it, it would be slowing it down. Got it? Okay? All right. So that is a important connection to the definition of work we've seen before, and a very important calculation tool for uniform fields. But let's say something that is a little bit more general, and that's these next two equations. They both start the same with the work done by the field, but their relationships to these changes in, well, energies are more general than a uniform field. And what do I mean by that? Well, I'm simply saying that the work energy theorem and the relationship between work and potential energy apply to work done by an electric field, just like with gravity, or for that matter, any field, okay? Or any force, really, okay? And to label things, okay, this right here is the kinetic energy, and this is the, well, change, of course, delta, the change in kinetic energy, and this is the change in the potential energy of the electric field, okay? This is just known as the work energy principle, and this is always true of work and its relationship to the potential, okay? Because this is the potential that's created by the force that did the work. That's why there's always a negative, okay? I always put it this way in the context of gravity, that if I lift something up, I'm doing positive work on the object I lifted up, but gravity is doing negative work because there is a gain in gravitational potential because it's higher. Got it? Okay. And it does actually follow from, of course, cosine of 180 degrees, right? Because they're opposite directions. All right, good. Now, two more equations down here. Because up to this point, notice we've been talking about energy a lot, potential energy, work, of course, being a form of energy, but we have not talked about voltage, despite making a big deal about defining it a moment ago. Well, we're getting there. Okay, so these next two formulas, work done by an external force and change in voltage, excuse me, they both also, as written, only apply to uniform electric fields, okay? That is, of course, a restriction, but a lot of times we work with uniform electric fields, okay? So this first equation here is the external work done to move a particle through a field, okay? It's equal to 1/2 mv squared, which is m for the mass of the particle, and of course, that term is the final kinetic energy, okay? And QED is the final electric potential energy. It's this term right here, QED, okay? It's QED looks a lot like MGH, as it should, because that was moving a mass through a uniform gravitational field, like on the surface of Earth, right? Where G was 9.8. So very similar idea, but now it's QED, okay? All right, it's good to see those parallels, good to get that familiarity, okay? All right. This term here, okay, is change in voltage, V for voltage, okay? Voltage also known as electrical potential, okay? And by definition, the change in voltage is the change in the potential energy, specifically the electric potential energy, normalized, which is jargon for divided by charge, represented by the letter Q, okay? And that means that change in voltage, since potential energy is QED, is just ED. Okay, it's just electric field times distance. All right, that's a very simple relationship. Change in voltage is just electric field strength times distance. Okay, now of course that only works if the electric field strength holds constant over that distance, which is why we needed the uniform part. Okay, but still comes up a lot. And do note that just as we were defining the work done by an electric field, the change in voltage can also be, well, okay, let me put it this way. The change in voltage is, of course, independent of the charge. That's the whole deal, because we divide by the charge that's moving through the voltage. Okay, moving across the voltage, however you want to say it. But if you want to, say, calculate the change in potential energy by saying that delta PE equals, I'm just cross multiplying here, Q times delta V. So maybe the thing we're solving for is the change in potential energy. So then we're multiplying a maybe perhaps a known voltage by a charge. Well, in that case, just as with the work done by the electric field, you need to know if the charge is positive or negative, because that will change the sign of your result. Because of course, moving a positive charge over positive voltages will increase its potential energy, but moving a negative charge over a positive voltage change will decrease its potential energy, okay? Because what is downhill for an electron is uphill for a proton, to use that elevation analogy. Okay, all right. So this next equation here is a useful generalization of all of this. Okay, here it is, relating the change in voltage to the work done by the electric field. Okay, all right. And it would be work done by the electric field divided by Q. I should have the normalization in here. I'll go ahead and add that when I upload the notes. So it should be a divided by Q. Okay, I just wanted to tie everything back together to show that these ideas are related. And of course, the negative just comes from, well, the definition, the relationship between work and potential energy. So now on to the next line, this one here. Okay, so this is a conservation of energy equation. You've seen the type, right? The KE1 plus PE1 equals KE2 plus PE2. That type of conservation of energy equation, okay? And we got an extra work term, external work, that could be in there too, okay? Here we're representing potential energy, not as QED, but we can. Instead, we're representing it as QV. But of course we can do that, because electric field times distance is just voltage. So we can write it however we want. We could write it as QED, right? Or I can write it as QV1. Just depends on the problem, the information that is available. Okay? And this equation here, this conservation of energy, this is important, applies to both uniform and non-uniform electric fields. Okay? Because although, I called attention to the fact that general definitions of work and energy applied to, all cases, applied to the electric case, we haven't really talked much about non-uniform electric fields. Of course, they're more complicated. How much will we talk about them? A little bit. And you'll see how and why in just a moment. But important to acknowledge that this general equation does apply to both. Okay? So this is general conservation of energy, and it can be used for the movement through an electric field with or without external work from pushing or even gravity. Okay? Good. All right. Now, this equation right here, what is this? This is new, okay? Because this is voltage, not change in voltage. And this is a very specific expression here. What is this? Well, this is specifically the voltage around a single point charge, and it is inversely proportional to distance. Okay? Now, that's because that's a great place to start, because any distribution of charge is some sum of individual charges. So in very simple cases, we can talk about having a few particular charges, like on the corners of a square or forming an equilateral triangle, just like we did with electric field and with, well, force, the Coulomb force, okay? So now we can do the same idea. We can build voltage maps from particular small groups of individual charges, okay? Now, why does this make sense? Well, it makes sense, of course, because voltage is energy divided by charge, normalized by charge, and that's what we're seeing here, all right? Now, the fact that we have a 1 over r relationship, I'm not going to be able to derive that, but I can show you a picture to justify it. So to show the picture here, we have a picture of electric field, okay? Electric field pointing away from a single charge. This is a positive charge, which is why the electric field points away from it. Of course, the electric field would point towards a negative charge. That's the way the electric field is defined, after all, okay? All right, we can interpret it differently for the two signs of charge, but it's always defined the same. So of course, here it's emanating away from a single positive charge. I've drawn different voltages, zoom in a bit on this a bit, V1, V2, V3, and V4 at different distances from that charge, okay? I'll talk about their player placement in just a second. And then there's some distance here represented by R for radius, just as it is in the formula, okay? Now this could be D, but it makes sense to call it R as a radius because we are always going to be moving away in a circular sense from an individual charge, okay? All right, so equipotential green lines, electric field purple arrows. All right. Now, we can consider a single cut down this line in gray, and then consider that cut as a graph of voltage measured in volts, I know it's funny, graphed against distance from the charge measured in meters. And we see that the voltage approaches infinity as we get closer and closer to the charge, because as we get infinitely close, we're dividing by a smaller and smaller number, so the voltage blows up, so to speak. And then we can see equally placed voltages at 1, 2, 3, and 4. So this would be, this one here would be 1, 2 would be here, then we'd have 3, and then we'd have 4, okay? So as we get further and further away, the voltages fall off. These are all evenly spaced, as I said, but then of course the distances aren't because there's that 1 over r relationship, okay? It's falling off like so, right? So that's the mathematical relationship. So finally, our last formula is just a way to convert energy from the traditional joules to an energy that's more well suited to the small energies of charges called an electron volt. All right, so that's an electron volt. An electron volt is a measurement of energy, and it's equal to exactly 1.6 times 10 to the negative 19 Coulomb volts, okay? Which is the same as saying 1.6 times 10 to the negative 19 joules. Now, the reason it's a convenient unit of energy is because it equals the energy to move one electron through 1 volt, okay? All right, so let's finally get on to our practice problems. We have 4 types of problems that I want to show you. Type 1, problems that involve calculating the work done by a constant force associated with an electric field or work done by an external force on a charged particle. Type 2, problems that involve the work energy theorem and relating kinetic energy and potential energy to work done in a constant and a uniform electric field. Okay? Then, simple problems that involve calculating change in voltage or a particular voltage relative to a point charge or distribution of point charges. And then finally, type 4, problems that involve conservation of energy, okay, to relate kinetic energy to changes in voltage in a non-uniform electric field. Okay, so this is a conservation of energy. Just left a word off. All right, example 1. Work is done by an external force to move a charge at constant velocity a distance of 1.4 centimeters in the direction of a uniform electric field of strength 1.3 times 10 to the negative 4 newtons per coulomb. How much work is done to move the charge if Q is 120 millicoulombs? Okay, so let's see. So here's the idea. We're moving a charge with the electric field as shown. Okay, excuse me for that. We're moving a charge with the electric field. Here's our positive charge. We're moving it in the direction of the electric field. Here's our displacement vector. Here's our force vector. And here's our electric field vector. Okay? All right. So what would this look like? Well, the work is equal to QED. Okay? Now, in this case, Q is positive. It's 120 millicoulombs. Okay? And we can think of the work done by the field as force times distance times cosine of the angle between them. Well, in this case, the displacement is parallel to the electric field, so it's cosine of 0, which is simply 1. So in that case, the work done by the field is equal to the negative of the work done to move something through the field. Now, is that always true? No, it's only true because here the net work is 0 because there's no change in kinetic energy, because we had that one key expression, constant velocity. That was really key for letting us know that we have a 0 net work by the work kinetic energy theorem, and thus our 2 works are the work done by the field and the work done by some external pushing force. Okay, why do I know there's an external pushing force? Well, there has to be because we're told there was. Okay, all right. So thus the work of the external force, you can think of it as a pushing force, but it could be anything, all right, is then equal to negative QED. Okay, in this case, again, Q is positive, so we're going to see how that works with our signs. That's going to give us our charge multiplied by our field strength multiplied by our displacement. Okay, convert everything to the correct units, and there we have a value of negative 2.18 times 10 to the negative 7 joules. All right, so that makes sense, right? That it's negative. But you might be thinking, but wait, we're moving a positive charge in the direction of field. That's positive. Well, that would be positive if I had asked for the work done by the field. But I didn't. I asked for the work to move the charge. So that means the work to move the charge is negative. Well, what the heck does that mean? Well, that means that there's some other force, we'll call it force external, that you have to be applying to your charge to prevent it from accelerating. Because after all, the condition said constant velocity. So that means we had to be applying the brakes the whole time so we could coast down the hill rather than speeding up as we rolled down the hill. Okay? All right. But anyway, let's go ahead and change the charge to negative and see what that does. Okay? So in this case, the work done by the field is FD cosine theta, but now for a negative charge, the thing that hasn't changed is the angle between the displacement and electric field is still 0 degrees because we are still moving in the same direction. Thus, the work done by an external force is equal to the negative of the work done by the field, which is the negative of the negative, right? Because now it's a negative Q, okay? Which means, of course, now it's positive work. Because now there's no need to apply the brakes, because to take a negative charge and push it in this direction, well, that is pushing it uphill. That does take work. It wouldn't go on its own. Got it? All right. Okay, let's look at a concept question. Okay, so part A of our concept question. As a positive charge, right, positive charge, is moved from position I to position F, so initial to final, is its change in electric potential energy positive, negative, or 0? And then what happens if it's a negative charge? So the idea here is initially I'm moving up positive from here to here, right, or actually from here to here. And then here, I'm going to be moving a positive from here to here. You get the idea. Okay, so let's run through the cases. All right, so in this case, the potential energy change is 0 because I'm just as far from the positive charge in both cases. Okay. In case 2, the change in potential energy is less than 0. Okay, I've lost potential energy because when a positive charge is very close to another positive charge, it has a long way to fall. Okay, as I get further and away from that positive charge, I have less distance to fall. Thus, I've lost potential energy. I've gone downhill. The further away I move from the positive charge, the more I've gone downhill. Okay, 3, this is an increase in potential energy. Okay, why is that? Well, because I started here and I moved to here. Okay, positive charge. Well, for a positive charge, a negative charge like this represents a pit. Okay, when I'm near the edge of the pit, I don't have that much potential energy because I'm already near the edge of it. As I move further away, I've moved uphill, thus gaining potential energy, the ability to fall further, as shown here, a gain in electrical potential energy. And finally, 4, here there is also a gain in electric potential energy. You might think it was 0 because we're along the midsection, but no, what's going to happen here is I start here where I am balanced out, but then I go uphill, all right? Actually, in this case, I'm going downhill. I go downhill because now the positive charge is just going to continue to get pushed away from the other 2 positive charges, but we've already started some of the pushing, okay? Whereas if I'm right at position I, I'm actually at a very high state of potential energy. I have further to fall. Now, interestingly, this actually is an unstable equilibrium point. So as long as I don't move at all as a positive charge, I could stay at that point. But as soon as I start to move a tiny bit, I would accelerate away and fall away from those 2 positive charges. Okay, now let's do it for a negative charge to move faster through these. So the change in potential energy for case 1 is still 0 because the distance hasn't changed. And now all the other signs are simply reversed because what was uphill for the positive charge is now downhill for the negative charge. So case 2 is an increase in potential energy. Case 3 is a decrease in potential energy. And then case 4 is an increase. See it? Okay. And just a label, this is for positive charge, and these cases are for negative charge. I think this is a good summary that you can refer back to remind yourself about the changes in energy as positive and negative charges move relative to charge distributions like these. Okay? All right, example 2. An electron initially has a velocity of 3.26 plus 8.12 kilometers per second. Well, 3.26 in the x direction, 8.12 in the y direction, units of kilometers per second. While moving through a uniform electric field of 0 in the x direction and then negative 9.1 times 10 to the negative 14 in the y direction. Okay? Now this is a very, very small force. I originally had a different value here, but it ended up being too strong. So this is our electric field strength here is very small. Okay? And then how much work will the field do on an electron after the electron has traveled 1.81 billion meters? The idea here is to think of this as a really weak field that exists in outer space somewhere. And this is an electron moving through a large distance of outer space, but through a very weak field. Okay? All right, so we need to find phi, the same phi that comes up in the definition of work, and do it by considering the components of velocity. But how do I know to take inverse tangent like this? Well, from the following picture. Okay? So I have the electric field pointed like so, and I have the velocity pointed like so. And actually here I want this, I'm going to make this positive, and I'll change that when I upload it because I solved the problem as it being positive, pointing in the positive direction. The negative would change the results, okay? And if I want to find the angle between my electric field and my velocity vector, then I can find that angle pretty easily by just considering the components of velocity, like so. And in fact, in that case, the opposite with tangent is the x component, and the adjacent is the y component. So then I can find my angle phi, and it ends up being 21.9 degrees. Okay? And then I want to find the work done by the field, which will be negative q, okay? Negative q because I have an electron, okay? So that's why, and here, notice I put that inside the parentheses to show that we've changed q to negative q, all right? And then I've got cosine of the angle between the 2 vectors, and then just their magnitudes. Okay, so then I put all my values in here, and there we go. This is the how much work the field did on the electron. The electron did negative work, or the field, excuse me, did negative work on the electron. That means that it slowed the electron down. It decreased the kinetic energy of the electron. But that makes sense because the electron had a velocity that had a component that was parallel to the field. It had no component that was anti-parallel to the field. Thus, it was slowing it down. Okay, it was applying the brakes to the electron. Okay, so then we're going to go ahead and look at our velocity here. Okay, so what I'm doing here is I'm just finding the magnitude of the initial velocity just by considering the two components of the initial velocity. Okay, and I converted it from kilometers to meters. All right, so I get 8,750 meters per second. Okay, then I'm going to use the work kinetic energy theorem. Then I'm going to use conservation of energy. All right, really, actually, I'm really still using the work kinetic energy theorem. I've just rewritten change in kinetic energy as the two full terms here. All right, then I'm going to solve for the final velocity and plug in all my numbers. Notice I plugged in the mass of an electron, the quite small mass, and I plugged in my my work done by the field. Okay, I almost said change in energy, but it's the work done by the field. It is negative because it is slowing the electron down. This is going to give me a value of V final that's smaller than V initial. Okay, and there we go, 4,780. So it has. So it's taken away about half its velocity. Okay, now did I need that number to answer the question because it asks for what is the final kinetic energy of the electron? No, I don't. I could have just not found the final velocity at all, but I wanted to at least show that step kind of as an extra bit of information. Now let's finally do what we were asked for, find the final kinetic energy. In that case, since I already know the final velocity, I can just plug it into the form of kinetic energy, the 1/2 mv squared, all right? And then here I just have a conversion factor where I'm converting from joules to electron volts, okay? Or yeah, from joules to electron volts. There we go. And so we get 6.51 times 10 to the negative 5 electron volts, okay? Now, hopefully that looks good in terms of our final expression of how many electron volts this has, okay? And let me make sure, oh, no, there is a typo here. I did some bad math because this is electron volts per joule, not joules per electron volts. No, that is joules per electron volt. Okay, because there's a tiny fraction of a joule per electron volt. No, actually, I think I overworried about it because this looks fine. And then if you think of the units, this expression is in joules. I cancel out the joules, and then I have in the denominator of the denominator the electron volts, so that actually is correct. And that makes sense because I'm dividing by a very small number, which is going to make this quite a bit larger, but the numerator is already so small, which is why my value of electron volts remains small. Okay, that actually does make sense. Good. Okay. All right, so example 3. An electron moves from a region of 0 electric field to a region of uniform electric field with a strength of 7.11 times 10 to the negative 5 volts per meter. Oh, let's pause and appreciate that. In the last problem, I expressed the electric field as newtons per coulomb, which is the way we've seen up to this point. But now look what I've done. I've expressed the electric field in terms of new units, volts per meter. Well, that's totally fine. Because think about the maps of equipotential lines. We saw that it was volts per meter that represented the actual relationship between volts, distance, and electric field. So we have two alternate ways of expressing the units, two very reasonable alternate ways of expressing the units of the electric field. Make sure to pay attention to that. Okay? All right. All right, and the direction is parallel in this case to the velocity of the electron. If upon entering the field, the electron has a velocity of 3.52 times 10 to the 6 meters per second, then what maximum distance will the electron travel before turning around? Okay, so very similar to the previous example, really, but just with some differences. I also want to point out that we've seen this problem before, but we solved it by finding the Coulomb force, then finding the acceleration, and then using kinematics to find the distance or the time, or whatever is asked for. Right, so you can completely do this problem using Coulomb force, Newton's second law, and kinematics of constant acceleration. Okay, but we don't have to. We can use energy instead. Right? Let's use the energy approach. So in that case, I just set up a conservation of energy equation. My initial electrical potential energy is 0, and my final kinetic energy is 0 because I want the electron to go as far as it can. Right, maximum distance. Okay, before it turns around. So then my conservation of energy simplifies to the following. Here's my kinetic energy term. Here's my electrical potential energy term, QED. Notice I'm not using volts because I wasn't given volts, so I might as well just use QED. Okay. All right, and it's a gain in potential energy. And there I'm just going to solve for the distance, and I get 496 kilometers, or 496,000 meters. Excuse me. Okay. All right, question 2. What is the ratio of voltage B over voltage A of the electric potential at the 2 points? All right. So this is the electric potential of a single point charge. This is where we'd have the equipotential lines that spread out, getting further and further apart the further away you go, representing that it's becoming weaker, okay? In the same way that you could draw the electric field, and then the fact that the electric field lines are becoming less closely packed together, also denoting the fact that the field is getting weaker, okay? The voltage is getting weaker, the field is getting weaker, the strength of the forces is getting weaker. Everything gets weaker the further away we move. But in this case, we're asked about the voltage. Now remember that the electric field strength and the force were inversely proportional to the square of distance, but not the voltage. The voltage is inversely proportional to just the distance, just the plain old distance, no square. So that's different. That's a different relationship, okay? So we want a ratio of our voltages. We use the formula for the voltage of a point charge, taking a ratio of the two different distances, R, B, and RA. Notice everything is like terms and cancels except for the distances. So then our ratio of the voltage at B over the voltage at A ends up being the same as the ratio of A over B. Notice that they flipped, okay? And that's then saying 1 millimeter over 3 millimeters, which is 1/3. All right. So the voltage from going from A to B, we have a 1/3 voltage. Okay. It's decreased by a factor of 3. Okay. All right. Next type of problem, example 4. A 15 nanocoulomb, so that's a billionth of a coulomb, charged particle moves from point A, where the electric potential is 300 volts, to point B, where the electric potential is negative 200 volts. By how much does the electric potential change? Okay, this is actually a very simple question. It's just a voltage change. V final minus V initial. Negative 200 is our V final. Our V initial was positive 300, so it's negative 200 minus 300, which is negative 500. We've had a voltage decrease of negative 500 volts. Simple as that, okay? We went downhill by 500 volts, okay? All right, and I show here that it doesn't matter what the equipotential lines look like. They can be weird shapes like this, but as long as this one is 300 volts and this one over here is 200 volts, then, and it doesn't matter what path we took, but as long as we went from I to F, from initial to final, right, then we had a change of negative 500, okay? It's just a scalar difference. It's not a vector, so nothing matters about the direction or how we got there. It just matters where we started and where we ended, okay? Now in part B, by how much of does the particle's electric potential change? Okay, well, it was a positive 15 nanocoulomb particle. So that means all we have to do is just multiply Q times delta V, multiply our positive charge by a negative voltage change, and we get a negative change in energy. Okay, does that make sense? Yeah, because for positive charge, going from high voltage to low voltage is like falling downhill. Okay, but how would your answer differ if the particle's charge were instead negative 15 nanocoulombs? Well, I bet you can guess it. In this case, Q is replaced with negative Q, shown here in the parentheses. So then we have a negative times a negative, which means the negatives cancel, and we have a positive change. Because for negative charges like electrons, going from high voltage to low voltage is uphill. I know I keep saying that, but that's an important idea to get. All right, so example 4. A particle with a charge of 5.5 times 10 to the negative 18 coulombs is fixed at the origin. A particle with a charge of negative 2.3 times 10 to the negative 8 coulombs, all right, so Q1, you notice Q1 is positive, Q2 is negative, is moved from x equals 3.5 to y equals 4.3. What voltage change does Q2 traverse? Okay, so here we're just going to look at the change in voltage, just use the formula. All right, so this is V final, this is V initial from a point charge, because after all, Q1 is our fixed point charge in this case, okay? Now notice that the change in voltage is going to be independent of Q2. We don't need Q2 for part A, okay? And so then I'll just have my change in voltage. I've just factored out the like terms of the electrostatic constant and the fixed Q1 charge, and here are my two distances. Notice that although I went from an x value to a y value, it doesn't matter because they're both effectively radii, right? So if this was my Q1, so essentially I went from this distance to this distance, right? But they're both a radius. So since I'm dealing with concentric circles, it doesn't matter that one is on the x-axis and one is on the y-axis, does it? Okay. All right. So in that case, I can just plug in the values of my final being 4.3 centimeters, or converted to meters, and then the initial being 3.5 centimeters converted to meters. All right, plugged in my other numbers, and there we have it, a change in voltage of negative 2,600 volts. Wonderful, okay? Now, what's the change in potential energy, okay? Well, the change in potential energy is PE final minus PE initial. In this case, Q2 matters, okay? because now I do care about the fact that I'm moving a negative charge, okay? So notice what I have here. I'm gonna have my Q2 and Q1. This should say Q2, okay? The correct value is written here. This is Q2, okay? It shouldn't, in other words, both these shouldn't be Q1. One of them is Q2, okay? I factor that out, okay? I also factored out the Q1 because after all, it was one of the like terms, okay? The electrostatic constant again. So basically the only difference between the two expressions is this one does not have a Q1 in front. The change in voltage does not, but the change in potential energy does, okay? All right, because voltage is independent of the charge that's getting moved through the voltage, where of course change in potential energy is dependent on the charge that's getting moved through the voltage change, okay? And so then I have a negative times a negative, and it gives me a positive change in energy, okay? Because again, taking a negative charge and moving it across a negative voltage change gives you a positive change in potential energy. You've gone uphill. I know you're getting tired of me saying that. Question 3. Points R and 2, the concept question, are each a distance d from each of the two particles with charges of equal magnitude and opposite sign as shown. What is the work required to move a particle with a negative charge q from r to 2, from r to t? 0, simply 0, right? Why? Because you didn't actually change any potential energy. It's the same potential energy at 2 as is at r. There's no change in potential energy, okay? Question 4. A particle follows the trajectory shown from initial position I to final position F. The potential difference delta V is what? Right, so I start here, I meander over to positive 50, I cross back over, and then I finally end up at negative 50. Well, okay, it's path independent. It doesn't matter that I went over here at all. It only matters the final state and the beginning state. All right, so the change in voltage is independent of the path. Delta finite is simply V final minus V initial. Okay, scalars. Okay, therefore the change is negative 50. Okay. Example 5. Two 5 microcoulomb point charges are 12 centimeters apart. What is the electric potential relative to infinity of this combination at the point where the electric field due to these charges is 0? Okay, so let's think about this. All right, I have a picture here. Okay, here's the picture, the same one that's on the beginning of the notes. Okay, this is a two like charges next to each other with the equipotential lines and electric field shown. And I want to consider the distance between them, d. I'm going to call this one charge 1 and this one charge 2. And then the point where the electric field is 0 is exactly between them. That's where it cancels out. Okay? We've done that before. We've shown that the electric field cancels out exactly between them. Does that mean that the voltage is also 0? In other words, is voltage 0 where electric field is 0? What do you think? Right? So we need to find the voltage at the midpoint between the two charges, because the midpoint is where the electric field is 0. Now I could show this more rigorously, but we've done it in previous notes. Okay, so then I just need to find the voltage at that particular point. Okay, and we can see that things are definitely not canceling out. Okay, in fact these two terms add together. So then that's my voltage at the point exactly between the two of them. Okay, Q1 equals Q2 equals Q, which is why I've just replaced it with Q. And so then I can plug in my values and I get 3 million volts. So definitely not 0, okay? But that makes sense because think about the map analogy. Just because you have a level bit of ground doesn't mean you're at sea level, right? You can have level ground at any elevation because that's all this represents is level ground. That's what because the electric field means there's no slope, okay? Well, electric field of 0 means there's no slope, but that doesn't mean your elevation is 0. In this case, that doesn't mean your voltage is 0. Got it? Okay. All right, final example. What is the electric potential at the center of the shown charge configuration? Okay, so how do we do that? So we want to find the voltage right here. Well, that's simply a matter of remembering the form of the electric or the voltage of a single particle and doing it for 3 of them. Okay, we've done it for 2. This first time we've done it for 3. 1 plus 2 plus 3. Okay, it's just going to look like this. All right. In this case, they're not all the same charge, so I can't factor the charge out. Okay. Whereas in previous examples, we were able to with 2 charges that were like charges. All right. And so then it's simply a matter of having an electrostatic constant in front. Consider the fact that they are all in units of millicharges. Let's see. So millicharge. No, the charges are microcharges. The Q4 that we're going to put here, that one is in millicharges, but these ones are all micros shown in the figure. I was looking at the body of the problem for the order of magnitude, but it's shown in the figure. That's where the 10 to the negative 6 comes from. Otherwise, all the values are the ones shown in the figure. And there we go. That is our voltage at this point, 125,000 volts. Okay, voltages do tend to be large, even for really small charges. And that's again because electrostatic constant is so big. Okay, all right, so that's part A. In part B, what amount of work would be required to bring a charge with a larger charge of 76 millicoulombs from infinity to the center of the configuration? So let's think about that, right? So would it be positive work or would it be negative work? Well, positive, because there's two positive charges here, and we're bringing another positive charge in. So even though the positive charge is attracted to this one, it's repelled by the two positive ones. So the overall force here is more repulsive than attractive. So it is effectively uphill, okay? All right. So the work of the field is the negative of the change in potential energy, which is the negative of the change in the voltage times the charge that you're moving, which is this one, Q4. All right? So then we take the negative of the change in the potential energy and the magnitude of the charge that's moving, the 76 milli, that's the 10 to the negative 3 coulombs, and there we have the work done by the field, negative 2,400, negative 9,470 joules. That's the work done by the field, okay? All right? So, but then the work required is the work of input is always equal to the negative of the work done by the field. Now, again, that's only true if the change in kinetic energy is zero, okay? But we definitely can assume it's zero because we're bringing something in and placing it. There's no mention of letting it fall. There's no mention of changing its velocity. So this problem very much implies constant velocity, okay? So that means that the work to bring that charge in from infinity is 9,470 joules. Because the idea is that these, from the point of view of this positive charge, these are two big mountains. This is a pit. And then over here at infinity is level ground. And we have to move uphill to get to this, this part, the foothills of these two great mountains to the side of this giant pit. Now, if we moved up the y-axis towards the pit, we'd eventually start going into negative, right, to the point where we'd have to be applying negative work input to prevent the charge from speeding up, but that was not the question asked. Okay, finally in part C, if Q4, which now we're giving its mass, is released, how fast will it be going when it returns to infinity? Because after all, these are the foothills. If you just let it go, it's going to roll back downhill to infinity over here somewhere, right? That's infinity, right? It's that far away. Well, in that case, it rolls downhill. As it rolls downhill, it picks up more and more speed. The reason we can find velocity infinity, which might seem like a weird idea, is because eventually it's picking up so much little extra speed that it asymptotically approaches a final velocity, kind of like a terminal velocity, okay? So the change in kinetic energy is just equal to the work of input, all right? So then we can find the final velocity by just considering the magnitude of the work input that we saw before. And so then it just ends up being this expression here. Oh, but I should have the square root there as well. The square root shouldn't just be on both ones. It probably got erased here. I'll fix that. All right. And then we have a final velocity of 1.26 times 10 to the 8 meters per second, which actually is almost half the speed of light. So we'd have to make a relativistic correction here. This is a good first estimate, but if we corrected for relativity, we'd find out that the value is actually slightly different. But we won't have to worry about that for about another 10 weeks. All right. So finally, a final couple concept questions to wrap up this lecture. Question 5. Atomic particles are often characterized by their kinetic energy in mega electron volts. What is the speed of an 8.7 mega electron volt proton? Now, you might think of this as more computational, but I just want to get it out there to get you used to the idea that we can often talk about the kinetic energy of particles in electron volts, and often mega electron volts. Okay, so we just set it up like this, the definition of kinetic energy. We're just going to solve for the velocity. It is 4.08 times 10 to the 7 meters per second, and then that is the same as 40,800 kilometers per second. Okay, notice here that I converted the energy over to electron volts with this expression right here. Okay, all right, question 6. 3 possible configurations for an electron E and a proton P are shown. Take the zero of potential to be at infinity, which is always a standard, and rank the 3 configurations according to the potential at S from most negative to most positive. Okay, so what I did here for all of these is I drew a graph of voltage versus distance with these lines lining up with points like the electron, the point of interest S, and the proton. So the idea from a kind of a side view, we see that voltage falls off to negative infinity as we get closer and closer to the electron. It has a midpoint between the two, because the voltage is in fact zero between two opposite charges. It's not zero between two like charges, as we saw in a previous example, but between two opposite charges, it does have a 0 point. All right, but then afterwards, then it goes uphill, approaching positive infinity as it gets closer and closer to the proton. In this case, S is closer to the electron than the proton, so it's in the negative region. It has a voltage less than 0. Okay? If we consider the case over here, it ends up being a different picture, but the same slightly negative voltage. Okay? Why is that? Well, because our distance from the electron and the proton are the same. So if we were to calculate it, we would get the same value. But graphically, we can see that we are in a region that is still slightly less than 0 because we approach the pit that is the electron. And then between the electron and the proton is just a squished version of this graph. All right? Basically, of this being a 1 over r squared, or excuse me, a 1 over r, and this one also having the slope of 1 over r. And then finally, we can consider the third case by kind of straightening it out, so to speak, and just considering it along a single axis rather than the two axes shown. And in that case, it's basically this picture again, but our S has gotten moved from here to here. And so there it is. It is actually in the positive range, the voltage that is, because we are closer to the proton than the electron. Okay? And that means we can rank our voltages from least negative to most positive, with 1 equals 2 and 3 being the most positive. In fact, the only positive. Okay. All right. I know it was a long lecture, but thank you so much for watching it. I hope there's been a lot of good information here, and I appreciate, or I look forward to, all the questions on this content. Bye for now.